Hello, everyone, and welcome to the Anti-Doping Podcast, brought to you by the Partnership for Clean Competition. I'm your host, Dr. Marie McNeely, and today we are joined by our guest, Dr. Frank Wojan. Listeners, Frank recently completed his PhD in clinical physiology at the University of Texas at Austin, and he's currently a senior clinical project manager with Pluto Health. And today we are excited to talk about Frank's career, his research, and of course, the project that led to his receipt of one of this year's PCC-sponsored anti-doping predoctoral awards in partnership with the American Physiological Society. So, Frank, we are delighted to have you here with us. How are you?
I'm doing fantastic. Thanks for having me. I'm really looking forward to this interviewing process.
Well, we're excited to have you here. We're excited to learn more about you and your work. So can you start by giving our listeners a little bit more information and just tell us about you?
Yeah. So as you mentioned, I recently completed my doctorate degree in clinical physiology from UT Austin. Pending that completion, I accepted a job offer with Pluto Health. It's a healthcare tech startup based out of the Raleigh-Durham area. It's a kind of spun out of Duke clinical research. And what we really focus on is integrating health information across many different silos, translating that, and then identifying healthcare gaps with medical records and the incorporation of other pharma or retail sponsors. So it's a pretty exciting job with a lot of implications to impact a lot of people for their health and wellness.
Very cool. This sounds like a fantastic opportunity. And I'm curious if we can rewind back a little bit farther. Frank, how did you first become interested in physiology and maybe touch into this anti-doping realm as well?
As many individuals, their process is a little bit convoluted and kind of takes a huge long walk along the trail, I guess, as a good analogy. But I started as a pre-PT undergrad. I actually did not get into PT school, which kind of directed me to seek out other opportunities. And one of those such opportunities was taking an exercise physiology class at Northern Illinois University, which was taught by Dr. Amanda Salazinski, who is currently at Westfield State University. And her colleague was Dr. Craig Broder, who owned a clinical research facility focusing on nutraceuticals and sports performance in Naperville, Lisle area, so Chicagoland. And based upon my interest, I was able to work with him, work with her, get into the master's degree program for exercise physiology, kind of develop my skill set, and then honestly follow the footsteps of Dr. Broder to UT Austin, where he got his PhD under Dr. Wilmore and some of the titans of the exercise physiology realm back in the late 80s, early 90s. He was a part of that and setting some of those studies up. So following his footsteps there, completing that degree, but really the approach that he took in training me, following my master's degree and what I would equate to a pre-doctoral fellowship, or at least the demands of postdoc life, where I was writing grants, completing research, securing funding, developing techniques, publishing works, all the demands of postdoctoral scholarship I completed before I got my PhD. So he took the approach of mentoring me as a master's level student, as a PhD student, and then with the expectation that you should operate during your PhD program as a postdoc and completing those subset of projects that are given to you during that time. So I learned a lot from him. I kind of really owe a lot of my success to him and Dr. Salazinski for finding my interest, shepherding it, and then also guiding me to where I am today and the critical thinking skills that coincide with that as well.
Fantastic. It sounds like you met some wonderful mentors along the way, and I'm curious to hear a little bit more about how the PCC fits into this picture. So, Frank, how did you find out about the PCC?
Yeah, so during my time at UT Austin, we routinely went to the APS conference, American Physiological Society. Unfortunately, due to COVID and the timing of when I was doing my PhD, we couldn't go for a couple years there because it got canceled. But it didn't preclude me from applying to some awards based upon my research that was ongoing or I'd recently completed. And one of the such awards was the PCC-sponsored anti-doping award. And while my research, which we can probably get into, doesn't really have so much applicability in anti-doping, the mechanisms at play that are involved with it definitely have some premise there or some purpose to really define some future implications for athletic populations and doping controls. So I said, let's take a shot. Let's apply. Let's see what happens. I mean, the worst that could happen is you receive a note. We awarded it to someone else and I was very excited to receive the award. I was not expecting to receive it, honestly, because of the clinical nature of my research, but very happy to. I spoke with Ryan Murphy, who is the executive director, after receiving the award and discussed the award process, what it entailed, and the rationale for why they selected me as one of the two winners. It was a great process presenting at the conference, learning more about it. I was invited to the conference that is hosted. So I was able to listen in a lot of the speakers and their presentations. And then, of course, presenting my work at APS under the sponsorship of the PCC. So it was really helpful, impactful. Outside of the monetary compensation that was associated with the award, just the exposure to bringing awareness to the work I've done, to the research that's currently out there, I think it's incredibly important.
Absolutely. And I'd love to get into your research. Now, I know you've focused on hypoxia. So to set the stage for listeners out there, can you just maybe start by explaining what happens physiologically under conditions of hypoxia?
So hypoxia as itself is really just a broad stimulus to affect the physiology, for instance, of humans in this example. So it's a physiological extreme and it has a lot of trickle down effects that are systemic in nature. So once you understand that component, there are a couple different varieties, just as there is different varieties of exercise training. We have HIIT training or you have steady state training. There are a couple different choices you can pursue with hypoxia exposure. The classical model is this continuous hypoxia, or go to an altitude training camp where you reside at altitude, hang out there for a few weeks, and then you train low or at a lower altitude. So the classical live high, train low philosophy. And then you go and do your competition, where my approach is this intermittent hypoxia. And it's a little convoluted within the literature because, again, definitions are not consistent there. But the term intermittent to me in my research is a short bout of alternating periods of hypoxia and normoxia, or sea level. So it acts similar to a HIIT interval where we have high intensity and then alternating periods of low intensity across a single session. So with that incorporation, we're able to set the difference between the continuous or a live high, train low philosophy, and then hopefully find some results, which we can discuss here soon, hopefully.
Absolutely. And I know as part of your doctoral work, as you sort of alluded to there at UT Austin, you created this novel hypoxic protocol that involves this intermittent hypoxia. So why specifically were you more interested in this intermittent hypoxia as opposed to like continuous hypoxia? And why did you want to create this particular protocol? And then what does that protocol actually entail from a sort of logistics perspective?
So upon my arrival at UT Austin, one of my lab mates, Sten Streg Gunderson, he's actually the son of the late Jim Streg Gunderson, who was one of the creators of the live high, train low philosophy there. So it was really cool to work with him. And I actually met Jim on a couple of occasions and picked his brain on some insights there. But really, when I came into UT Austin, I had a little bit of exposure to intermittent hypoxia without really calling it intermittent hypoxia during my master's thesis. But my advisor, Dr. Sophie Lalonde, was interested in developing this intermittent hypoxia protocol as a means to serve a clinical function or to improve clinical outcomes. What is little known about this intermittent hypoxia has been around for some time. The Soviets developed this, intervention. But what was not really great about their protocol design is they didn't have a lot of control groups. The results are kind of hidden. They're not published in westernized journals, so they're not recreatable. So we can set out to kind of really define that and improve its utility in some of these clinical populations. So when I came into UT Austin, a previous student had tried to undergo this intermittent hypoxia exposure, and then it wasn't successful. So upon immediately entering in, I took it under my scope, my project, kind of did the literature review, kind of understand where the gaps were, where we could improve, where we could modulate the protocol to really get a desired outcome, which was an increase in erythropoietin or EPO, and then subsequently try to get an increase in hemoglobin mass or red blood cells. So the approaches that we took here were modulating the intensity and then the timing domain of these HIIT-like intervals. Again, there's no exercise involved with this. It's literally sitting down, passively resting and breathing a hypoxic air that's manually titrated to a certain fraction of inspired oxygen or oxygen percent. And then we approach that. We're starting to get a targeted oxygen saturation that we can just measure via a pulse ox to see a change there. And we're really interested in these alternating periods. And that alternating period is really what sets it apart from the continuous or a live high, train low philosophy. You're able to get a higher intensity. You're able to get recovery periods. And then the effects of this are you're able to trigger erythropoietin to be stimulated without the concomitant decline in plasma volume that really is shown in this long drawn out altitude camper or live high, train low philosophy.
Oh, very interesting. And you mentioned that one of the variables in particular that you were modulating or trying to pinpoint where the optimal point was intensity of hypoxia. And I know, obviously, if you push it too far, there's some serious negative effects from not having enough oxygen in the moment. How did you determine kind of what was a safe or reasonable intensity to try to target?
So you get some deleterious effects with going to kind of an extreme oxygen percent or our FiO2 fraction of inspired oxygen. Roughly, I think it's below 10%. You're really getting the onset of some of those extreme outcomes that are deleterious. So we really hovered around 11 to 14%. With that said, though, we really weren't focused on that percentage to a certain degree. We were really focused on the SpO2 or that oxygen saturation. There's a little bit of work out there that indicates that you have better responsiveness in regards to creating erythropoietin if you were to measure the intensity by the internal stimulus. And that internal stimulus would be the SpO2 or oxygen saturation measured by a pulse ox instead of just controlling for the ambient FiO2, which you're breathing in. So we're able to control that intensity with each cycle or each interval and allow them to resaturate back to normoxia or sea level air in between these alternating periods that are roughly 4 minutes in length. And then the specific protocol, which is carried over into all three of my dissertation studies, is defining this 8 cycles of 4 minutes of hypoxia, again, at a targeted oxygen saturation of roughly 80% is what we're shooting for, interspersed with a brief period to resaturation. So that resaturation period on average took around 2 minutes. It's different for everyone, but it kind of matches up with circulation time in the resaturation component. But that alternating period is thought to be the trigger for a host of transcription factors, HIF1 alpha and HIF2 alpha to be precise. And that triggers the cascade of erythropoietic events, triggering EPO to be produced. And then hopefully over time, we're able to get an increase in hemoglobin mass or red blood cells from that stimulation.
Definitely. And I know science sometimes involves a lot of trial and error. And you mentioned there's a number of different variables here, whether it's the interval time, the number of cycles, the intensity, all of these different things. How did you go about designing and testing and coming to the conclusion that this was the optimal protocol for you to use?
It took a lot of trial and error piloting. I think piloting is a critical step in all of this. We really went into looking at the protocol and deciding what variables there we can manipulate. And to guide us is we didn't really want a long drawn out protocol that would expand multiple hours of someone undergoing this. We want it to be practical for use. So what could we modulate within an hour time frame? Well, we can modulate the intensity to a certain extent before we start seeing some of those deleterious outcomes. We can modulate the hypoxic time. But the really critical component here is we want to understand this dynamic of triggering HIF1 alpha and HIF2 alpha, these transcription factors. And it's thought this repetitive nature of going up and down with this hypoxic intensity is thought to trigger that stabilization of the HIF a little better and then build it over the whole hour in length, which would equate to an EPO or erythropoietin creation. And then subsequently, we could increase red blood cells over time.
Very interesting. And of course, you tested this first in healthy people before moving to clinical populations. So what were your findings, Frank, in terms of the erythropoietic outcomes in these healthy populations?
So as I mentioned, there's 3 separate studies that I conducted during my dissertation there. And the first was trying to figure out what happens in healthy younger individuals. And what we found from this 8-cycle protocol was there was a 65% increase in erythropoietin with this intermittent hypoxia approach. But what was more important from that finding was that it was no different than 120 minutes of continuous hypoxia exposure. And the previous research that's been out there that shows the minimal effective dose to produce erythropoietin in humans is this 120 minutes of continuous hypoxia exposure. So the fact that we're able to produce a similar amount of erythropoietin in a third of the time, honestly, is pretty impactful. Now, we didn't measure red blood cells during the study. In hindsight, we probably should have, but under the guise of trying to get this pilot, which turned into the study actually prior to COVID, that was our outcome. So we are able to demonstrate we increased erythropoietin from this, and it's turned out to be the shortest hypoxia exposure amongst the literature to produce this increase in erythropoietin in healthy young individuals.
Very interesting. And to make this kind of anti-doping or sport connection, then how might this intermittent hypoxia protocol then help improve performance for an athlete?
So that's a Pandora's box type question with a lot of different outcomes there. So this approach really hasn't been utilized in athletics. It is an aim of mine to kind of incorporate it into that population. But if we look holistically at the benefits of if you were to develop this intervention and do it, say, every other day for 2 weeks, some of that work has been done in clinical populations, and we've seen the same amount of increase in red blood cells or hemoglobin mass as we have from the live high, train low philosophy, which is 3 weeks at greater than 2,100 meters and no less than 14 hours a day. So you're really sleeping in an altitude tent. And the benefit of this intermittent protocol is the fact you don't have the concomitant plasma volume decline. You're actually increasing hemoglobin mass, and you're having the maintenance of an increase in plasma volume, which would further impact cardiac output and improve VO2 max. Whereas that continuous live high, train low philosophy, you have the increase in hemoglobin mass, but you also have a decline in plasma volume, and the cardiac output effects are negligible. You stay the same for the most part. So your performance is elevated because you're able to increase oxygen carrying capacity. But with the intermittent protocol, you can increase oxygen carrying capacity and increase cardiac output and increase VO2 max. So if you were to strategically implement this in athletes, you could do it over, again, the period of 2 to 3 weeks every other day with minimal amounts of exposure and try to get that increase in red blood cell mass.
Very interesting. And I guess if we were to be kind of maybe doing a side-by-side comparison, we've mentioned this live high, train low paradigm a couple times during our conversation. I guess if you had to look at the pros and cons of your intermittent hypoxia protocol versus this live high, train low, what are some of the differences?
Again, it's unproven the amount of increase in hemoglobin mass that can be obtained in an athletic population. You're really dealing with athletes who are already erythropoietic developed, is a great way to put that, I guess. They're closer to their genetic potential with the amount of red blood cells and hemoglobin. So it remains to be seen if you can actually increase that in that population. But a clinical population that is at a lower level, they're able to increase by the same amount as that continuous live high, train low philosophy. But to answer your question, it really relates to less time involved, and you can direct your training elsewhere. You don't need to go live at an altitude training camp. You don't need to go do that before, say, the Tour de France. You don't need to go train at an altitude camp to get the red blood cell adaptions, at least. You can do this every other day. And then you also don't get the decline in plasma volume that is typically seen in that live high, train low philosophy. So there are a couple of benefits there for athletic populations.
Oh, very interesting. And have you pushed this to the point of seeing ceiling effects where after you do this for X amount of time, the benefits are diminishing?
Yeah, I think once you get closer to the genetic potential, it's different for everyone. I don't think a ceiling has been defined. Now, there are ranges that we've seen the max amount in normal individuals who have a genetic component that allows them to be higher. But to be honest, I don't think it's really been defined. In the same vein, I don't think there's been any research to my knowledge that has really shown hemoglobin mass changes over like a multiple tour stage event. Whereas the biological passport and several other indices that measure blood doping, they measure hemoglobin and hematocrit. But both of those metrics are really susceptible to hydration and fluid volume shifts. And notably, Lance Armstrong back in the day was doing saline infusions to dilute his hematocrit level and hemoglobin as well. So hemoglobin mass, which is what we measure in the older study that I completed and the patients with type 2 diabetes study, it's really resistant to fluid volume shifts. So it would serve as a great metric to assess the utility of red blood cells over a certain time frame. Could be a multiple tour stage event, could be throughout the course of a year, but it actually measures the actual mass of hemoglobin instead of the component of fluid volume and those.
Oh, very interesting. And we mentioned a couple times now that your work, of course, has clinical relevance as well. And I'd love to dig into that. So, Frank, can you talk a little bit more about your findings in this more recent study in patients with type 2 diabetes?
Yeah, I actually like to start off with just highlighting the older study real quick, because we've taken this successful protocol in the healthy individuals and we incorporated it into a healthy older group. And then as well, as you mentioned, in type 2 diabetes. The fact that in the older group is we actually saw a 34% reduction in the amount of erythropoietin that was created within this older group. So these are healthy individuals who are actually relatively fit. So if we were to measure their erythropoietin, they increased 31% from this intermittent hypoxia protocol, same protocol as the younger individuals. But when we take that to a population of type 2 diabetes, we actually found no increase in erythropoietin from this identical protocol, which is incredibly surprising in some regards, but unsurprising in others, because this population ultimately with the disease progression may become anemic. So that may be a causation or early indicator of trending towards anemia or this erythropoietin deficiency, or at least production deficiency that may lead to that anemia later on. So the fact that we're able to see that, I guess, failure to increase erythropoietin in this population from this protocol, we know that increases erythropoietin is pretty important. I will say that within this type 2 diabetes study, we also measured hemoglobin mass, the metric I've already mentioned. And to be honest, there isn't any measure out there of hemoglobin mass in patients with type 2 diabetes. There's a few studies that have measured it in type 1 diabetes, but none in type 2 diabetes. And the reason, I guess, the rationale we wanted to integrate this into type 2 diabetes is really because there seems to be a 20% reduction in hemoglobin mass and blood volume affecting this group. So we're comparing this to an older group of similar age-matched body size related individuals. Patients with type 2 diabetes typically exhibit a 20% decline in red cell mass and blood volume. So this is hypothesized, and we're actually able to confirm that with this study as well. So we're seeing this disparity. We're seeing that there may be a causative factor here. They may be unable to produce erythropoietin at a much earlier stage under the trigger of a hypoxic stimulus.
This is very interesting. And I know it's kind of the early stages of this work, but thinking big picture here, Frank, what are some of the potential impacts of this line of research?
So I think the implications of this type of protocol would be fantastic to incorporate in patients with type 2 diabetes. Again, over a multiple week protocol, it would kind of attenuate some of the declines in VO2 max mediated by an increase in red blood cell quantity to bridge the gap between type 2 diabetes impairment and the healthier older individuals. So they may be more reluctant to start exercise, patients with type 2 diabetes, that is. So this may bridge the gap and allow them to develop those habits and routines to facilitate greater overall health and wellness. But from a sports perspective, I think that researchers should really investigate the implications in athletic populations. What would it take to increase this red blood cell mass in athletic populations over a multiple tour stage and prep for that? I know that Jim Strait-Gunderson and Ben Levine at UT Southwestern, kind of the founders of this live high, train low philosophy, did some work in this. It's unpublished. But what they found was that it had no real effect in this population. But they really didn't focus on too much of the protocol per se with this alternating intermittent hypoxia exposure. It was more along the lines of doing a continuous hypoxia for 90 minutes and multiple days and seeing the outcomes there. This HIT-like approach with this intermittent hypoxia really wasn't examined. And I think that would be a take-home point to go and see what the effects of that were in an athletic population and see if there's some implications there, especially because of the deleterious effects that can occur with that live high, train low philosophy with the decline in plasma volume and really no change in cardiac output. If you can mitigate a plasma volume decline by undergoing this type of protocol, you can really see some performance improvement happen here and then ultimately win stages or win competitions from this.
Certainly. I think this has really important implications for anti-doping in sport. And you mentioned, of course, the clinical side of things. You targeted type 2 diabetes. Are there other conditions that you would be interested in testing this protocol with that might have similar problems, whether it's anemia or some of these other issues that could be alleviated by the effects of this protocol?
Yeah, so two main groups that have been done with kind of a longer protocol by Martin Bircher. I believe he's based out of Austria, but they incorporated patients with COPD and elderly patients with coronary artery disease. So two lower fitness populations that could benefit from exercise or exercise adaptions. So incorporating this protocol, because it's a systemic stimulus, acts similar to exercise and the benefits from that. So if we can incorporate this without exercise, we can really see some of the benefits and develop those within those populations that are experiencing low fitness or low VO2 max or low red blood cells. Those populations specifically. But you brought up the anemia component there. That's difficult to understand with the anemia component because there are a lot of factors that go into play there. A lot of molecular mechanisms like hepcidin and inflammatory cytokines that may attenuate some of the erythropoietic capacity or increases triggered from intermittent hypoxia. So there's a lot of redundancy built into human physiology, and it's hard to kind of pick and choose which one takes precedence under certain conditions and see if we can really correct anemia with this philosophy. If I was a betting guy, I would assume that we could probably do that if inflammation is mitigated or attenuated in some way, shape, or form. We could probably do that. But again, it's a question that still remains to be studied, I think.
Absolutely. It sounds like there is still a lot of exciting work to do in this particular area. And I know earlier this year, you received, as we mentioned, one of the PCC-sponsored predoctoral research awards in collaboration with APS, the American Physiological Society. And you, of course, presented work from your research in type 2 diabetes at that annual APS meeting. So I'd love to talk about that experience. You mentioned it a little bit at the beginning of our conversation, but what was it like for you actually going there, having these results to share with the scientific community there?
I was very excited to attend that conference. It's more of the scientific conference. A lot of molecular mechanisms are discussed here in contrast to, ACSM, where it's more exercise and broad approach. So this is really why we choose to go to this meeting and attend it and see the molecular mechanisms associated with physiology. We think we're more in line with that, or at least our lab was. But the experience itself was fantastic. Presenting at a conference, getting to describe your results to people via a poster, but also via a EEP sprints. So the EEP is Environmental and Exercise Physiology section of APS. What they did this year was incorporate a new competition. It was themed the EEP sprints, where we had, I think it was 2 minutes to describe our research.
Oh, wow.
Not a whole bunch of time to do it. So just hitting on the highlights, crafting a narrative, creating a story that people could take with them after that effect. And it was great. I enjoyed speaking that. I enjoy public speaking. I taught at UT Austin from lecture halls of like 200 people or small lab settings of 15 individuals. And I enjoy that dynamic. It was fun to discuss my research with my peers and have an audience there to listen that was aware of the physiology and the science behind it. Whereas students may not understand or grasp the full entirety of what you're trying to tell them. It was really cool to have that experience for sure.
Well, that sounds amazing. And I know the future is bright for you here, Frank. So what are the next steps for you, or maybe the next steps for this particular research?
So the next steps for me are continuing my work with Pluto Health, but also I work again with Dr. Craig Broder there out of Exercising Nutritionally Chicagoland. I still have a partnership with him. So we're still doing performance studies, nutraceutical studies, investigating some of the similar things that I worked on previously. So that's an ever evolving thing. I know he's close to retirement in some regards, but he may be moving down here close to me and we might start up a new research facility in Raleigh, Durham. But that's really what I have going on. But the research itself, there's a lot of unanswered questions within the literature. A lot of the mechanisms at play, again, I alluded to the redundancy that exists in human physiology. Understanding that redundancy could have some drastic implications for the anti-doping scene, or understanding the interactions with molecules in regards to red blood cell creation a little more in depth. Some of the molecules or mechanisms that I think warrant further investigation are hepcidin, erythroferrone, EPO, and then of course hemoglobin mass or total hemoglobin mass. Those metrics themselves, I think, are really understudied and serve as a basis to understand the doping scene and track individuals who may or may not be doping. If we can really understand those dynamics, then we can pick apart and see maybe a little easier who is doping and who is not. So there's a lot of implications still in the red blood cell creation literature.
Absolutely. And I think some people may be surprised to hear that there are still so many unanswered questions in physiology. But I think you're absolutely right here with clinical physiology, exercise physiology. There's so much that you can add to the anti-doping conversation. So taking a step back, Frank, can you maybe just talk about some of the important contributions that people in the physiological field can contribute to anti-doping science and some of the important reasons that they should be involved?
I think continuous further development is always necessary. Exercise physiologists, at least taking a step back from the academic model, is they're really trying to investigate certain mechanisms or isolated mechanisms for improvement. So it's in the athlete's interest to really get exercise physiologists on their side, but also they're finding these mechanisms that could improve their performance, but they're also finding these mechanisms that contribute to anti-doping science. So they're able to bring awareness to certain mechanisms. And then now we can develop tests that will test for that mechanism and then maybe weed out who is doping, cheating, all those different components of doping in competition. So I think it's extremely valuable to keep the relationship with exercise physiologists going. I know that in the US scene, it's more clinical shaped. Overseas, Europe, it's more sports performance based still. So I think there is some utility to really providing funding, which the PCC does. And I give them credit for that. It's awesome that they are a funding body for exercise physiologists because it's definitely warranted within the US that we need to go back to our roots and go to studying exercise and athletes because that's going to dictate a lot of clinical implications along the way and not focus so much on the clinical aspect to a certain degree. I know the funding kind of shifts you there with the NIH, NSF, all those different funding bodies, but to have the PCC as a partner in this to really allow faculty members or researchers to get funding to do these type of things, I think continues pushing the narrative forward, building the science, building the literature, and then opening doors for a lot of different individuals.
Oh, absolutely. I think the PCC is a critical piece in continuing to foster this interdisciplinary nature of anti-doping and anti-doping science and continuing to make advances on a variety of different fronts here. And I know science isn't easy. As we alluded to, there's some trial and error. There was this whole process involved in sort of even getting to the point where you could have an official study going. And I know, Frank, these can be difficult as an early career scientist. So for you, what were some of the biggest challenges that you have faced as an early career scientist?
You're kind of on an island with your own scientific approach. Like you have to be supportive of your own work. You have to advocate for it. So some of the difficulties or challenges is really the acceptance of your scientific approaches. And the biggest acceptance that you could be awarded is a bigger grant. So an NIH grant or an NSF grant. Those are kind of a external validation that your research is warranted and valid. So really the profession within academic model is shifting towards a publish or perish. And if you don't get funding, you perish type of mentality. So I think we need to take a step back from that and really see if that's healthy for our discipline, but also take a step back and also understand that just with study design, one of the biggest downsides to research in this model is a lot of the old school frame of thought was you really want to understand a single variable over time during a protocol and isolate that variable specifically. But there are unique ways that you can integrate in secondary variables that would provide optional avenues of support later on for if the main outcome wasn't solved. So you could tack on a lot of these secondary outcomes or measures without interfering with that original outcome to try to solve some more problems. So stack in more there. And then if your main outcome doesn't work out, you have other paths to go on. So I think that's one of the things that's missing a lot in academia is supporting your research with other avenues to go after you've successfully defined an outcome or failed to get the result that you wanted. So those aspects really need to be approached and changed, I think, within academia.
Definitely. I love this strategy that you've described for study design, kind of having these built-in backup plans, because I think you're absolutely right. Like so many things that you do in science sort of don't turn out the way you expected, or there may be some problem or another, or even you might just uncover something really interesting by kind of having these different pieces built into it.
That's definitely the approach. I mean, if you're outside of the academic model, I mean, you're in a industry model, you want secondary backups there to have funding available for other projects. So this is one of the big things that I learned from Dr. Broder while working with him is don't put all your eggs in one basket, because at the end of the day, you may lose that basket or they may all get cracked, right? So you want to have multiple baskets of eggs, right? That's the goal, right? And then you can dictate where the narrative goes with the outcomes you get. So definitely supporting yourself, advocating for your research, and having backup plans integrated into your protocols without convoluting or messing up the primary outcome. It's very easy to do. And I think it's one of the most underutilized protocol approaches that affects our discipline right now.
Certainly. And I know there's a lot of limiting factors when it comes to doing science, whether that's limited funding, just time, the feasibility of the projects you're trying to do. All of these different things often hold you back. So, Frank, if we took off all of the barriers, all of the limiters, and you could do anything, you had all of the resources you could dream up, is there one particular problem in anti-doping or exercise physiology that you would most want to solve?
First and foremost, that'd be fantastic. I would love that for that to happen. But I mean, in a real world, that won't happen too much with the barriers in place, rightfully so, with IRB submission, funding sources and stuff. But really, if I had all the resources imaginable, I would really want to investigate some of the things that I alluded to earlier, which was investigating the responses of hepcidin, erythropoietin, erythropoietin, hemoglobin mass, maybe over short and long-term study. But secondarily, the magnitude of blood doping expressed from the metric of hemoglobin mass in elite athletes really hasn't been published at all. I alluded to earlier that traditional metrics of hematocrit or hemoglobin concentration are susceptible to these fluid and hydration challenges or changes. So having a metric in place that you can't modulate with chugging down a bunch of water or taking a saline infusion to manipulate that metric is really critical. And I don't think this metric has been utilized in any shape or form over a competitive season, let alone multiple tour stage or competitive season for an athlete. So I think it'd be a really easy study to do, to be honest, but I think that needs to be done so you can see the true effects of someone blood doping, or if you can really weed out for those individuals who do or don't, and then integrate in those secondary objectives, like I alluded to with hepcidin, erythropoietin, EPO, alongside that analysis. So that would be the cool study to do, I think. And also, it probably could get approved pretty easily. So if someone out there wants to do that, hit me up and we can coordinate on that.
Well, listeners, take note here. If you are interested in pursuing or supporting this project, it is ripe for the picking here. And Frank, if our listeners want to learn more about you and all the amazing work that you've done, what is the best way for them to do so?
So you can find me in numerous places. Google Scholar, my research is there. PubMed also. You can find information about my partnership with Dr. Craig Broder at enllc.us, or Exercising Nutritionally is the company there. You can find me specifically on Twitter, or I guess now X, at Wojan. Really simple there, just F and then my last name. You can find interesting stuff from articles I've posted there, my published papers, I repost there.
Excellent. Well, listeners, definitely get connected with Frank. Take a look at his work if you haven't already. And Frank, it's been such a pleasure to have you on the show today. Thank you so much for your time.
Thank you so much. And thanks for listeners chiming in and listening to this podcast. I think it's a great resource. And I want to thank the PCC for their continued support and obviously the award that was presented to me as well.
Well, congratulations on everything again, Frank. Thank you so much. And listeners, it's been wonderful to have you here with us as well. And we would appreciate it if you could take a moment to rate or review our podcast on your favorite platform. And listeners, please note that the Anti-Doping Podcast features a wide variety of clean sport experts, and episodes may include statements and or viewpoints that do not necessarily reflect the views or values of the PCC. Thank you, and we look forward to seeing you on the next episode of the Anti-Doping Podcast.